All right, this is Mr. Anderson for Kellogg Community College. Buckle in and get ready for part 4 of Chapter 2, Section 5, looking at cotangent, tangent, secant, and cosecant graphing with changes on amplitude, cycles or periods, and also a vertical shift. So we're going to be doing a lot of big work here today. And after we're done with each of these problems, we're going to deal with domain and range. So I first want to write down the cotangent of x formula, just so you can see how this is moving. This cycles every 180 degrees, so this is going to be pi, and this is going to be 2 pi, which normally my secant, cosecant, sine, and cosine graphs will go to 4 pi because that will be 2 complete cycles. This actually will show 2 complete cycles this way. It crosses the x-axis at pi over 2 and 3 pi over 2. So let's draw the picture here. There's one, and here's the other. One of the special points is at pi over 4, and that's really going to intersect there at 1, and this is 2 pi. 3 pi over the 4, 3 pi over 4 here, which is going to be at -1. So for our first modification to our parent function, we are going to multiply by 2, which is going to change our amplitude. Now what I like to do is, instead of making the graph look twice as big, I'm just going to copy the same graph and let the points do the talking. So this is going to be pi, and this is going to be 2 pi. Again, this is pi over 2 at 0, 3 pi over 2 at 0, and here we have the same graph, but you'll notice that my point here is at pi over 4, comma 2 on my y-axis. This is pi over 2, comma 0. This is 3 pi over 4, comma -2. 4 pi over 4 is obviously pi. Then 5 pi over 4, comma 2. This is 6 pi over 4, or 3 pi over 2, comma 0. And then 7 pi over 4, comma -2, and then 8 pi over 4 is 2 pi. Well, now what we're going to do is we're going to subtract 1. Now, what some people teach is that they decide to teach by moving this, but this is kind of a little trick I use. I am going to keep the picture in the same position, but instead of this being 2 and -2, I'm going to drop it by 1, so this is 1 and this is -3. Now you might be wondering, well, how does that work? Well, how it works is that I can put in little tick marks over here and I'll adjust where my x-axis is. But to be kind of accurate here, you can see where I'm going to use that old x-axis to mark my points like I do here, but instead of, since this is a 1 instead of a 0, the new x-axis is right here. There's our new x-axis right there. So be understanding that when you drop the line, it looks like the water raises up 1. So now, instead of this being pi over 4, comma 2, this right here is pi over 4, comma 1. And since I want 5 points here, I'm going to kind of go through this. This is going to be pi over 2, comma -1 instead of pi over 2, comma 0. And then this point over here is going to be 3 pi over 4, comma -3. Notice our points usually went from 2, 0, -2. Now they're all down 1. Hey, we've got a little asymptote line here. This beautiful asymptote line is at pi, this is at pi units here, so this is going to be pi on my x, y equals just pi right there. Almost drew a denominator for no reason. There we go, so x is equal to pi. And then we're going to, let's see, 1, 2, 3, 4. Let's do another point here. This is going to be 5 pi over 4, comma, and just making sure this is 1 right there instead of 2. And then, of course, we can keep going. This is going to be 3 pi over 2, comma -1. This is going to be 7 pi over 4, comma -3 here. And then the asymptote line is x equals 2 pi. Well, that, my friends, is our cycle. But our 2 cycles. Let's go and talk about domain. Domain are all of the x values, but you notice that it can't be pi or 2 pi, therefore 3, 4, 5, 6, 7, 8, 9 pi, all the way to infinity. So x cannot be any k pi, where k is an integer. That means for every positive and negative whole number, including 0, this is going to be your exclusions. Now for our range, I'm not going to screw this up here. Our range, since it can be infinitely high and low, we can say that this is going to go from negative infinity to positive infinity, like so. All right, so 1 down, 3 to go. Okay, so for our next problem here, we're going to actually not need all 3 pictures here. We're just going to use 2 of them. The big twist in this picture is this kind of a funky, this is a funky omega that's going to change the way we look at the period. Well, first of all, though, let's go and rock our asymptote lines. The asymptote lines are at pi, 2 pi, 3 pi, 4 pi. And here we go, turning them around at 1 and negative 1. So we can see that. All right, now what I'm really going to use in this problem here is I'm going to use the first 2 intervals, because this is going to be pi over 2, and this is going to be x is equal to pi. Now what this means is I need to make some adjustments for my, my period there by taking my interval, pi over 2, and divide it by omega. Now dividing by 3 pi over 2 is the same as multiplying by 2 over 3 pi. What this is going to do is the pi's are going to simplify. The 2's are actually going to simplify, which leaves me with 1/3. So in the same picture, obviously I'm not actually going to try to bust out my art skills and make this look, you know, longer, more or different. I am just going to do a little twisty-turny and say that this is not going to be pi over 2. This is going to be 1/3. 1/3, comma 1 in this case. So this intercept, or this asymptote line is actually at x equals 2/3. Because we got, this is 1/3, this is 2/3, and at 3/3, or 1, this is going to be at negative 1 on my y-axis, or y height there. And then this would be x equals 4/3. So 2/3, 4/3. And the reason why I'm doing this is because there's kind of some interesting pieces of this problem right there. This is going to be, this is 5/3, comma 1. So 6/3, again, this is going to be the asymptote line of x is equal to 2, because 6/3 is 2, and then this would here be 7/3. This is really interesting when we're not going to need that because we're actually done graphing this function. Let's talk about our domain. Our domain is where x is going to be x, but not the values of 2k over 3. Now what's nice about using 2k is then you can say k is an integer. Now what's important about that is that this will give you basically 2/3, 4/3, 6/3, and I think there might be some question about why couldn't I just say x cannot be k over 3 if k is an even number. Well, technically 0 is, or k has to, 0 is technically neither even nor odd. So when we talked about the odd numbers, it passed over 0 in those cases. But in this case, you got to be a little different about that. You could say, I guess, k over 3, but you'd have to add some more words in there to say that 0 over 3 also would not be included. So you can add that in there if you want to. But this is what the book says, and I can see their point. The range is going to be the set of y values where y is going to be greater than 1 and less than negative 1, so, or equal to negative 1, or y is greater than or equal to 1, because it turns on that point for those problems. All right, 2 down, 2 to go. All right, we'll be using all of our faculties for these 2 problems here, so here we go. let me get the pen turned on, and we are going to graph the parent function. The parent function, like the cotangent on the previous page here, kind of wish this was a tangent now, just so you'd see the difference here. This is going to have an asymptote line at pi and 2 pi. Oh, sorry, is that right? Pi and 2 pi? Yeah, that's right. Just second guess myself for a moment. So this is the cotangent function, like so. Again, now kind of wishing I made this a tangent problem so we would have, you know, one of each in this video, but that's okay. Now let's change the amplitude on us right here. This is 3 and -3. Again, not trying to bust out any art skills here. We're just going to try to make it so that you can see that at pi and 2 pi, it's going to work. Now this is pi over 2, this is pi, and actually I'm sorry, the dot should be about right there at pi over 4 for that location, pi over 4 comma 3. So my line didn't go through the dot that it should go through. That's where it should go. Sorry about the little like line right there. Now what's important about this is I'm going to mess with my omega here. Pi over 4 is the first interval in my x-axis, so I'm going to divide by my omega. Dividing by 1/2 is the same thing as multiplying by 2. So what I have here is 2 pi over 4, which is pi over 2. So now I'm going half as fast, so this is going to stretch everything out twice as long. All right, so what that means is that I'm going to plot my points for my cotangent. All right, I'm going to do it like that, have my intercept there, and I'm going to try to be very accurate and honest about this before we get to that -2. So here's my cotangent graph like so. All right, so at that point, this is still 3, and this is still -3, which will change for our last step here. But this is not going to be pi over 4 anymore. This is going to be pi over 2, comma 3, that point right there. And this is going to be pi, comma, or pi, yeah, I almost made a denominator there. Pi, comma 0. This is going to be, since this is pi over 2, this is pi. This is going to be 3 pi over 2, comma -3. And then this asymptote line is going to be x is equal to 2 pi instead of pi, because we're actually slowing down the line so we actually get there in twice as much distance. So if you had graphed this over this, it would look, let me change colors here just to show you. Now the line would look like this. Whop. And then you would see that it would have its points here and here. But I like doing 2 cycles on the same graph and let the points do the talking. I've had some people email me and ask, like, why don't you make your students, you know, show your stretch and shrink and stuff? And this is just a philosophical difference that I like to let the graphing calculator do all that, because you're paying for the technology. Why not let it do it? Now, this is another part where some people might disagree with me and say, well, you should have them now physically shift the graph down too, but why not just change the axis like so? Now, what this will do is it'll change, since you're dropping this, this is going to drop your graph. This is going to raise the pool water here. See if you make 2 tick marks here, 3, 2, 1, 0, 1, 0, -1. So this kind of puts things in perspective there. So you can put your 2 tick marks above and below that line. I would copy your problem before I would make the new x-axis. So now what you have is you have your points for your cotangent, like so. But now you can easily label your points, because this is pi over 4 comma 1 instead of pi over 4 comma 3, because it dropped 2. This right here is going to be pi comma -2. So our new x-axis is right there. And this one way down here, this is 3 pi comma 2 comma -5. And then we have an asymptote line at x is equal to 2 pi. And then this over here is going to be, since we're moving by halves here, and I just realized now I put pi over 4. That should be pi over 2. So let me change that to a 2. Pi over 2 comma 1, pi comma negative 2, 3 pi over 2 comma negative 5. So we're moving by halves. So this is 4 halves. This would be 5 pi comma or over 2 comma 1. 6 pi over 2 is the same thing as saying 3 pi comma negative 2. And then this point here is going to be 7 pi over 2 comma negative 5. And then we have the x, or the x value for the asymptote line is x is equal to 4 pi, which is going to be 8 pi over 2. All right, one more problem to go, and you've been holding on really well. Let's go take a look at a secant problem. We took a look at we had a cosecant problem at the top of the page. So now let's rock a secant problem. There is going to be a asymptote line at x. Sorry, not x. Wow. At pi over 2. So every pi over 2 units, there will be every pi over 2 plus a pi 180 degrees, there will be an asymptote line. So what this is going to give us, oh man, I forgot to do my domain and range of the previous problem. Nuts. Okay, so in the previous problem, sorry, I'll do this here. My x, since this is cotangent, x is not going to be any 2 pi k's where k is an integer. And this is another problem where you may have debated and say, couldn't I just say that this would be pi k, where k is an even integer? But again, we run into the 0 problem. And since it's cotangent, the range is real. All right, back to this problem. Sorry, I moved that up before doing that there. So what we have here is a secant problem that starts at 1, just like the cosine graph. So off it goes. And it turns around and swoops down from the top at 2 pi. Right there, there's 2 pi, comma 1. And here we are, 3 pi. This dot right there is 3 pi, comma 1. And then it ends at 4 pi, comma 1. So what we'll do is we'll do the same graph again. Some students in my class were wondering if they could just start with this graph instead of doing this one. And that's fine. I think actually, you know, manipulating the number in front, the a value, also known the absolute value of the a values of the amplitude. Doing that is oh no, I put my asymptote lines in the wrong place. Oh poo. There's not a real good way to kind of get rid of those. So what I'll have to do is just put these in here. Maybe I'll start a new color. Yeah, ignore the blue. Go to the green. All right, so pay attention to the green lines. Do not pay attention to the blue lines, even though they stand out 1,000 times better. All right, so here's my little twist and turn. Pi, this is pi comma 3. This is 2 pi comma, or pi comma negative 3. This is 2 pi comma 3. This is 3 pi comma negative 3, and this ends right here at 4 pi comma 3. All right, let's move on to another color. All right, back to blue. All right, so no more mistakes here. Asymptote lines are rocking at each of these positions, but now we have to mess with the omega, which is going to affect our shift, or sorry, not shift, affect our period or cycle. So what we notice is that our first significant place is this x equals pi over 2 asymptote line. So if that's the width of one gap there, I'm going to take that gap and divide it by my omega to figure out the size of the new gap. Now dividing by 1/4 is like multiplying by 4 over 1. So this is going to be, instead of pi over 2, it's going to be 2 pi. It's going to be 2 pi. So this is x equals 2 pi, which is crazy because this graph just got slower. It just got super slow. Now compared to where the 2 pi was, the 2 pi was like in the previous graph, if I'm going to change my color again, this is 2 pi here. Now the graph is going like that. So instead of having this, this is now 4 times wider, since we're going a quarter as fast. So it's, you know, a lot of this, my students and I really spent more time in class. So this is something to kind of really hammer out with your students if you're doing this with them. This is the point 0, 3. and then this is going to turn around at 4 pi comma -3. Whoa, right? And this is going to be 6 pi right there. This is x equals 6 pi because every interval is now 2 pi wide. And then this is going to be now 8 pi comma 3. And then this is going to be x is equal to 10 pi, so on and so forth. There I got my 5 points, or 5 spots on the graph. And now what we'll do is we're going to shift this up 1. Now, again, instead of me moving everything up 1, I like to copy the same picture but change this to a 4 and change this to a -2. What this means is I've raised this up, so that's going to drop the water level. So what I like to do to make my new x-axis is I kind of measure things out. This is -3, -2, -1, 0. I'm going to put 2 tick marks here, and I'm not going to draw my new x-axis until I'm done copying my picture. So here's my picture. Starting here, it's going to swoop up. So that's the point 0, 4. This is still x equals 2 pi. But when I do my swoop here, my swoop is going to be at -2. So this point right there is going to be at 4 pi comma -2. My new x-axis is driving right through here. It's 1 unit lower. So that's not going to hit any dots in particular, but it just does kind of drop it gives you that eyeball look where the graph has actually moved down. Let's go swoop right there, and this is going to be 8 pi comma 4. And then again, these x asymptotes, these x lines do not change because this is a shift up and down, which doesn't shift it left or right. That's for the next section. So now let's just plot this last point in here. All right, this is going to be 12 pi, since this goes 2, 4, 6, 8, 10. This is going to be 12 pi, comma, -2. All right, domain and range. Didn't forget about it. Domain and range. Okay, so in this case, it looks like we're going to have our asymptote lines again at every single, in this case we're going to go odd because this is pi and this is 3 pi, this is 5 pi, this is 7. These asymptote lines are at 1 pi, and let's see here, did I mess up? Oh, looks like our asymptote lines, hold on a second here, our asymptote lines are again going to be the same as before, where x, because it looks like we're at 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. These are our asymptotes. So we're going to go 2 pi k, where k is an integer. Because in this case, we got, 2 times 1 is 2. 2 times, ooh, I guess I can't say that, can I? 2 pi k. Okay, so this is going to have to be 2 to 6. Maybe this is going to have to be 1 and 3 and 5. Oh, k has to be, k is an odd integer. There we go, k is an odd integer. So this is 1 times 2, 3 times 2, 5 times 2. Sorry about that, almost made a little mistake there. And then let's look at the range. The range is going to be that, not all real this time because there's a gap between this dot at 4 and this dot at -2. So our range is going to be the y values where y is less than or equal to -2 where it turns around, or y is greater than or equal to 4 at that turnaround. Whew, one take. Made only a few little quick brain mistakes there, but I think this gets the tough problems done here. Thank you for watching, and if you have any questions, just email me, and I'll see you in class.